Welcome back, Physics 11, our last video of the week on introducing a new force. And to be honest, this isn't really a movie about a new force or a clip about a new force. It's about applying a force that we've just learned about, tension, but in a specific context of something that's being pulled up or being pulled down, and in terms of whether it's staying at a constant velocity or whether or not it's accelerating. So just a quick reminder, tension occurs within a material that is being pulled or stretched. And as we discussed in the previous video, it acts at all points along the rope and in both directions. Remember, I gave the example of you have a train of people all holding hands, and the two end people are being pulled. Well, everyone along the middle is also going to feel that tension. Everyone's going to feel that tension in both directions. Now, when a person is accelerating upwards or downwards in an elevator or anywhere else, they can sometimes feel heavier or lighter than they actually are. Now, their actual weight, remember, weight is just another word of saying force of gravity. So weight, force of gravity, same thing. Their actual weight is the same. We know that G equals m times g. Well, if you're moving up in an elevator, your mass certainly hasn't changed. G certainly hasn't changed. You're still on Earth. But your apparent weight can differ. Sorry, I think I misspelled that here. Apparent weight. Okay, so apparent weight is how heavy we feel is actually equal to the normal force. So let's think about that for a moment. Let's say you have a scale and you're standing here, and as you're standing on the scale, it tells you that your weight is, say, 500 newtons. Now that's accurate because you're stationary, and we know that the two forces acting on you, Fg, which, let's say you're around 50 kilograms, this is going to be 500 newtons. Because you're not accelerating, your normal force is going to be the same as that, so your normal force is going to be 500 newtons. Now let's say someone incredibly strong lifted the scale up with you standing on top of it, and they quickly accelerated that scale upwards with you standing on top of it. Well, would the scale reading still remain at 500? No, it certainly wouldn't. You can imagine someone's pulling up quite quickly, that scale value is going to jump. Even though your force of gravity hasn't changed, we know that the scale is changing, and so that kind of shows us that that scale is representing how much upward force it is applying on you. So we can see that the normal force is actually the apparent weight, or how heavy we feel we are. We suddenly feel more pressure on our legs, so we're going to feel like we're heavier, although obviously we're really not. So for this part here, the mass in the elevator, this is just a thinking exercise. So what you're meant to do is think about places you could be in the elevator when, and these are scenarios whether it's moving up, moving down, accelerating down, etc. If you're getting faster, getting slower in the upward or downward direction. When would you feel, or when would you appear to feel heavier than normal? What are two cases when you would appear to feel lighter than normal? And what are three times when your apparent weight and actual weight are equal? So pause the video, see what you can come up with for these 7 different answers here. So 2 times when you feel heavier, 2 times when you feel lighter, and 3 times when you feel the correct amount. Your apparent weight and your actual weight are equal. So hopefully you've had a chance to pause the video and you have thought about this and given it some thought and got some preliminary answers on there. So let's see, what are some examples when we would feel heavier? Well, one of them would be when we start moving upwards. So let's say you get on the ground floor and it starts to move upwards. Well, at that point, you're going to feel a little bit like you're being pushed to the bottom of the elevator. You're going to feel a little bit heavier. And one other time when we feel heavier is when we stop moving down. So if you are riding down the elevator and all of a sudden it comes to a stop, again, you're going to feel suddenly that you're a little bit heavier. You're going to feel more pressure acting, pushing down on you on your feet. So these are both times when you would feel heavier. When it starts to move up, you'll kind of feel squished to the bottom of the elevator a little bit, and when it's moving down, you come to a stop, you're going to feel squished a little bit. What about appearing lighter? Well, one of those would be when we start moving down. So if you're up on the penthouse suite and all of a sudden it starts dropping down, you're going to feel a little bit lighter. You're going to feel like almost like you're being kind of pushed up towards the top of the elevator. And another case is when we stop going up. So if you're riding the elevator upwards and then it comes to a stop, all of a sudden you feel a little bit lighter on your feet. And 3 times when you would feel the same, well, the obvious one is if you are stationary. And then the other 2 are constant velocity down or constant velocity upwards. So let's think about what these mean. What do these 2 here have in common? Well, if we think about the acceleration of the mass, in both of these cases, it is going to be a positive acceleration. So when you're going from stationary to moving upwards, that's going to be positive. And if we want to prove this mathematically, we can think about it this way. We remember that acceleration is v final minus v initial divided by time. So if we start moving up, we're going from our v initial is 0, and then our v final will be some non-zero number. Let's say we're going to deal with 2 meters per second. So this will be 2 minus 0 divided by time. Well, that's always going to be a positive value. What about when you stop moving down? Well, in this case, when you stop moving down, your final is going to be 0, and your initial is going to be negative something. We'll call it negative. And so again, what are you going to have here? 0 minus negative 2 divided by time. That's always going to be a positive number, right? So it's always going to be a positive number for this scenario. When you start moving up or stop moving down, your acceleration is always going to be greater than 0. What about when you feel lighter? So again, if we look at this before, when you start moving down, so v naught is 0, and v is going to be some negative number. So you're going to have negative 2 minus 0 divided by time. That's always going to be a negative number. Put that up here, negative 2 minus 0 divided by time. This will be negative. When you stop going up, that means your final speed is going to be 0, and your initial speed was something positive, like 2. So again, 0 to minus 2 is always going to be a negative number. So in this case here, your acceleration in both of these scenarios would be negative. And lastly, when you're stationary, obviously those 2 forces are equal. When you have a constant velocity downwards, again, you're going to have your no acceleration, and that means that those 2 forces are going to be equal and opposite, and obviously same thing for constant velocity up. So acceleration is equal to 0. When the acceleration is equal to 0, you are going to feel like your actual weight and your apparent weight are the same. Okay, so 4 quick questions. We're going to try these one at a time. I'll go through the first one, and then you can try the other 3 on your own before you can look at my results if you were unsure of that. So a 65 kilogram person in an elevator traveling upwards at 5 meters per second. What is their apparent weight? So the first thing we should do is we should draw our free body diagram. In this case here, we've got FG and we have FN. Now in this case here, it says they're traveling up at 5 meters per second. So 5 meters per second, it doesn't say that they're getting faster, it doesn't say that they're getting slower, so that means it's constant velocity. And so we can look at our diagram and realize that our normal force is equal to a force of gravity. In terms of its magnitude, this is equal to m times g, which is going to be 65 times 9.8, which is going to be equal to 637 newtons. So again, you're looking at this diagram to see if they are equal or unequal. So try the next 3 on your own. Pause the video here and try these next 3 on your own. There will be some acceleration for some of these. So in this case, you will need to do this sort of idea here, where there are mass times our acceleration is going to equal the sum of all of our forces, and we need to identify what those forces are. So pause the video here, give these 3 questions a try, and come back when you're done. Okay, so let's take a look here and solve our answer here. So the first thing I'm going to do is draw a free body diagram. In this case here, there is a force of gravity, but this says that they're accelerating upwards. So if they are accelerating upwards, it means they're not equal and opposite forces. And in this case, if we're accelerating upwards, that means that our upward force has to be the larger of the two. So Fn is going to be larger than Fg. We know that so far. So what is the apparent weight? Well, the apparent weight is again the normal force. So let's look at our formula here. We know that m times a is equal to our net force. And our net force is another way of saying what we get when we add all of our forces together. In this case, there's just the two, Fn and Fg. So 65 times was our mass. We're going to multiply that by our acceleration. I'm going to call it upwards positive. That's kind of a normal thing to do. That means that our normal force is going to be positive and gravity is going to be negative. So 65 times our acceleration is equal to the normal force plus force of gravity. Now we saw in the previous question that the force of gravity is 637, but we have to take care to include the correct sign. And so if Fn we're calling positive and the acceleration we're calling positive being upwards, then our gravity would be negative 637. So 65 times 4.9, I'm going to add 637 to both sides, and we'll get the following. Fn is equal to 65 times 4.9 plus 637, and this is equal to 956 newtons. So there's our answer for the second one. For the third one, we have a downwards acceleration. So the downwards acceleration here is going to be, let's see if we draw a free body diagram. We've got force of gravity here. And would our normal force be greater or smaller than the gravitational force? Well, in this case here, it's reaching the top floor and decelerating. So that means we're going upwards and the acceleration is in the opposite direction, which means our downward force is going to have to be the bigger of the two forces. So our Fn is going to be smaller. And we can go back to our trusty formula that we have here, which is mass times acceleration is the sum of our forces, which in this case is our normal force and our gravitational force. So 65 times negative 4.9, remember, we have to remember that it's a negative acceleration, is going to equal our normal force plus our force of gravity, which we've already seen is negative 637. So if we rearrange here, add 637 to both sides, 65 times negative 4.9 plus 637 equals our normal force, and this is equal to 319 newtons. So this completely jives with what we've been thinking before. We're accelerating downwards, we're going to feel lighter. We're accelerating upwards, we're going to feel heavier. And when we're not accelerating, as in example 1, we're going to feel exactly what our weight really is. Okay, so here we go. Last one here, number 85, or number example 4. An 85 kilogram person goes from the top to the bottom floor, and we want to find their apparent weight when they are accelerating downwards at 3 meters per second squared, when they're constant velocity of 12 meters per second downwards, and when they have an upwards acceleration of 3 meters per second squared. Same kind of idea for all of these here. So mass times acceleration is equal to our sum of our forces, which is equal to our normal force plus our gravitational force. So in this case here, we have 85 times negative 3 equals our normal force plus our force of gravity. So if we go back to our free body diagram, we'll just draw it out to the right over here. We have our gravitational force and our normal force. Now the normal force may change for these three scenarios. So for when it's accelerating downwards, we know the normal force will be smaller than gravity. Constant velocity, those two will be the same. And upwards acceleration, the normal force would be the larger of the two. We can calculate the force of gravity for all three of these problems. Remember, that's not going to change. So this is equal to m times g, which is going to be 85 times 9.8, and that is equal to, let's see, 85 times 9.8, it's going to be 833. So that's the magnitude of our force of gravity. But remember, for all of these three questions, that's going to be considered a negative force as it's downwards. So this is what we are left with here. 85 times negative 3 equals a normal force plus negative 833. And so this is going to give us a value of, well, 85 times negative 3 is negative 255 equals our normal force. I'm going to add 833 to both sides. Plus 833. And this is going to give us 578 newtons. That's our first one. For our second one, we know it's going to be moving at a constant velocity, which means our normal force and our gravitational force will be equal because our acceleration is going to be 0. We can still do this the same way that we've been solving them up here. And let's just try that just to kind of prove a point to ourselves. In this case here, mass times acceleration equals our normal force plus our gravitational force. In this case, actually, let me just change pen color here. We have 85 times 0, because that's our acceleration, equals normal force plus gravitational force. And so, again, this kind of shows us that our normal force and gravitational force will be equal and opposite if it's a constant velocity, if there's no acceleration. And we've already determined what our gravitational force is. It's 833, and therefore our normal force equals 833 newtons. Highlight that one. And lastly, we have an upwards acceleration. So for this question here, we have 85 times positive 3. I'm just kind of emphasizing that positive. You always don't have to write it that way. Equals our normal force plus our gravitational force, which we've seen already is negative 833. 85 times 3 gives us 255. We're going to add 833 to both sides, and that's going to give us a normal force of 1,088 newtons. Okay, so feel free to pause, play, rewind this clip here, see if you have any questions about it, or as always, save them for an X block and you can ask me then, or you can ask me on Monday. Hopefully you found this informative. The second page of this is going to be for your homework, so you can make sure you get that done for class. All right, thank you.